You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. We're now going to spend some time learning about static analysis. The static analysis can be seen as an end in itself, or it can be seen as a means of providing a good stable starting point for a dynamic analysis. A static calculation can be specifically run from the calculation menu, the icon in the toolbar, or the F9 key. But it will, by default, always be performed even if you go straight to dynamics. So, regardless of your purpose for using OrcaFlex, it's important to master the skills involved in achieving a stable and consistent static system equilibrium. First of all, we're going to look at a model which has been set up to allow us to assess the static calculation in more detail. As we start, it is worth remembering that the static calculation is split up into 3 stages. The first 2 of these relate to all of the lines in a model, and the third analyses the system as a whole and is called whole system statics. The model we're using is that of a calm buoy system, which includes a number of mooring lines, an offloading hose, a ship tie, a tanker, and a 6D buoy representing the floating calm buoy. It has been deliberately set up to calculate statics slowly to allow us to review the process as it is happening. So let's take a look at that model now. I'm going to use a workspace file to give me 2 views of the model. One side elevation and one plan view. The plan view shows us we have an array of 6 mooring lines for the calm buoy, with a vessel sitting in a southeasterly direction relative to the buoy. You may notice I have a compass in my plan view. This is something that can be enabled on the drawing page of the general data form. Its orientation is also defined here. If we run statics, the first thing I'd like to draw your attention to is the status bar. This shows us the progress of the calculation through a series of messages. This information often changes quite quickly, so it can be difficult to digest what is happening when you see it one message at a time. If we click on the status bar, this opens the statics progress window, a text window where we can see all the messages from the statics calculation. It can be printed, exported to a text file, or copied. We can see the calculations that are being run on the lines in the model, and once whole system statics has run, we will see the iterative calculations for that stage also. Having closed this window, it should be noted that it can be reopened by either clicking on the status bar during or after the statics calculation, or if the statics calculation has moved on to dynamics, it can instead be opened from the window menu. So, the first 2 stages relate to lines. But what are they exactly? Well, the first step is a first guess for the positions of all the nodes in a line in order to provide a good starting point for step 2, an iterative calculation for equilibrium for all the nodes in the lines. Step 1 is performed on each line one by one, as can be seen from the statics progress window, followed by step 2 for each line. These steps are performed with the line ends and degrees of freedom for all other objects fixed. Once static equilibrium has been found for the lines, all degrees of freedom are released and a static analysis for the whole system is performed, aptly named whole system statics. For this case, the release of degrees of freedom allows the vessel to rotate to its true equilibrium position. Let's reset the model and take another look at the analysis as it happens. We're able to control which stages are performed to help us look at what is happening, and this is sometimes useful if you're trying to diagnose a problem in statics. I'll go to the statics page of the general data form and firstly deactivate whole system statics by unchecking the box here. Next, I will set the line statics step 2 policy to none. This lets us run statics and only include step 1 line statics, which I will do now. Looking at our statics progress window, it says that whole system statics was not performed, all lines were excluded from step 2 statics, and catenary statics was successful for all lines. Catenary statics was the chosen method for step 1 statics. Let's look now at where that is defined. On the line data form, let's take the line called first more. There is a section in the centre right for static settings. Here we see the methods chosen for step 1 and step 2 statics. You can see that catenary is selected for step 1, full statics is selected for step 2, but this setting is overridden by the global setting on the general data form, where we set the line statics step 2 policy to none for all lines. In terms of model behaviour, when we've only selected step 1 line statics, there are a couple of things to note. Firstly, you will see that we have seabed interaction for the mooring lines, indicated by the white line nodes. Secondly, the buoy and vessel have not moved at all between the reset state and statics complete. This is because in step 1 line statics, the degrees of freedom for all objects except line nodes are temporarily fixed. Now we'll reintroduce step 2 line statics and see how things are changed. We'll go to the general data form and set the line statics step 2 policy back to solve coupled systems and run statics again. Now, if we look at the statics progress window again, it starts to show full statics successful for each line as it is run. The success, or otherwise, of that line statics step 2 stage is dependent on the line statics convergence settings assigned. Often these can be left at the default values, but we'll see in a moment that sometimes this can result in a line statics failure. I mentioned previously that this model has been set up to run deliberately slowly. This has been done by increasing the damping on the line statics convergence page, and once the static calculation has completed, we'll take a look at that page. OK, with statics now complete, we'll open up the line data form, and here are the damping settings. Note that this is damping of the static calculation, not physical damping in the model. OrcaFlex includes an automatic damping system, but you can define the minimum and maximum damping factors. Increasing these has the effect of reducing the step taken at each iterative stage, thereby providing improved stability, albeit at the expense of convergence speed. The default damping values are a minimum of 1 and a maximum of 10, and we have settings of 100 and 1000 here, and this is why the calculation takes a while to run. I'd like to return the damping settings to their default values. This could be done on each line data form, one by one. However, there is an easier way, which is a good opportunity to introduce you to the All Objects data form. This is accessible from the model browser and is a form which contains all the data from all objects in a model. It's a really useful form when you want to change multiple sets of data at the same time, which I can demonstrate now. I want to change the line statics convergence settings for all lines, so I'll make sure Other Data is selected, then select the Line option, and below that you will see the pages from the line data forms duplicated, and if I make sure I select the statics convergence page, I have a list of all the settings for all the lines. This gives me a couple of useful options for quickly editing the data for all the lines at the same time. The first option is to modify the top row as required. Setting these values back to default. Then highlighting and copying the data down using the Excel copy down shortcut, Ctrl D. Note I changed the maximum iterations to the default value of 400 as well. This value is the number of steps the solver can take in order to find equilibrium before the calculation is abandoned. It is used for both line statics, shown here, and whole system statics. If the system has almost found equilibrium when it reaches this number, simply increasing it can sometimes be enough to complete the calculation. In our case here, as I said, we'll be returning to the default value of 400 steps for each line. I'll just cancel that form and go back in to show you the second option, which is to highlight all the data that I want to change, and in the context menu select the option Set Selected Items to Default. This is a new way of setting default data in version 11.1. You'll see that, having edited the All Objects data form, the model has automatically been returned to the reset state. Now, when we run statics again, things seem to initially run quickly before we run into a problem with the line 6th more, where it appears to get stuck at an error of approximately 0.1 before eventually failing. If you have a situation like this where the calculation is tending towards a low error before getting stuck, this is often an indication that more damping is needed. So let's try to increase the damping for that line. On the statics convergence page of the line data form for 6th more, I'll slightly increase the minimum and maximum damping to 2 and 20. And that results in a successful solve. We've still only completed the line statics stage since we had turned off whole system statics. Let's go and reintroduce that now by opening the general data form and selecting whole system statics enabled. Now when we run statics, the line statics stage happens quite quickly, but at the whole system statics stage we once again have a deliberately slow calculation. The whole system statics convergence parameters are controlled from the statics page of the general data form. And as with line statics, the min and max damping is high at 10 and 100 compared with the default 1 and 10. If we set these values back to the default, again we can highlight them and use the context menu to set selected items to default. And if we run that again, we should see a calculation which runs nice and quickly. We've learned that increasing the damping adds control, but at the expense of speed. To achieve an efficient calculation speed, it's best to find the smallest damping level that still results in convergence. But what will happen if the level of damping is too low for the system? As my model is quite stable, I'll need to cheat a little to demonstrate this by setting very low levels of damping that I would never recommend using. The purpose is to show you visually what happens when there isn't enough damping. I'll go back to the general data form and reduce the max damping from 10 to 1 and run statics again. Now we have chaos. If you ever see this, I would always recommend trying higher damping levels in the first instance. As well as the damping, we can also control the number of iterations for whole system statics. As with line statics, the max iterations value is the number of steps the calculation can take before it is abandoned. The default value is 400, but we have a large number in this case to allow for the slow calculation caused by the high damping values. Although we've now returned the damping to the default values, there will be no detrimental effect from leaving the max iterations at 5000. The solver will only take as many steps as it needs to find equilibrium. Another parameter in the statics convergence settings is the tolerance. This is the allowable error in the solution and therefore controls the accuracy. A larger tolerance will be easier to solve, but will lead to a greater error and therefore less accurate solution. The default tolerance value for statics is 1e to the minus 6. This is a value which has been arrived at with years of experience, so should be changed with caution. If you need to adjust the tolerance to achieve statics convergence, this would suggest there is something else in the model which needs to be optimized. As an example of how changing the tolerance can have a detrimental effect on solution accuracy, we'll increase the value on this model to 0.1. Before I do this, note the position of the vessel. Let's run statics now. So after statics is completed, we can see the vessel hasn't moved to its true equilibrium. The allowable error was large enough for OrcaFlex to regard the initial vessel position as a valid equilibrium. Finally, I'll return the tolerance back to the default value. Remember, I can do this by using the context menu. One final part of the static calculation I'd like to demonstrate is a setting change that can be helpful for line statics in certain circumstances. Take for example this scenario where I would like to model an umbilical cable lying over a lifting quadrant, modelled with elastic solid shapes. With the default convergence settings, the line doesn't get lifted up in statics, since the program has no way of knowing its intended placement. So we need to give it a hand by showing where we want the line to be placed. And this is where the spline starting shape comes in. If you recall, line statics has two steps, and the first of these is where we specify the starting position of the line. The default step 1 method is catenary, which for our line means it is hanging below the seabed. When statics is run, reaction forces on the nodes lift them up to the surface of the seabed, at which point a valid equilibrium is found. Instead, we're going to use the spline method to give the line a better starting point for the iterative static calculation. When this is selected, you'll see an additional white line drawn in the view with some white crosses adjacent to it. During step 1 line statics, OrcaFlex will place the line as close as it can to the spline shape, so we need to position the spline above the quadrant and allow it to fall down onto the quadrant in step 2. This positioning can be done by dragging the crosses, the spline control points in the 3D view. Sometimes this approximate positioning can be good enough, but we can also specify Cartesian coordinates for each control point. This is done on the line data form on a new page called Spline Starting Shape, which appears when the spline method is selected. On this page we can also add extra control points to allow a more defined spline shape to be created. For this example, I've already defined some control point positions in a spreadsheet, so I'll go and copy this data now. Note that when I paste, the program sees that I'm adding additional control points and suggests increasing the number of rows. I now have 4 spline control points, and I'll try running statics again. Okay, that's not much better. When using the spline starting shape, we sometimes need to consider a different step 2 line statics convergence method called magnitude of standard error and magnitude of standard change, which gives us a couple of extra controls on the convergence. This is found on the statics convergence page of the line data form again, and I'm going to select this now. I'll reduce the magnitude of standard change from 0.2 to 0.01. This is a way to reduce the iterative step size even more than is possible with damping alone. Running statics again, we see an instant solve with the line now in the correct position. So that's a basic introduction to statics in OrcaFlex. For more help on common statics convergence issues, I would encourage you to take a look at the Statics Convergence Guide, available for download from the resources area of our website. We're going to move on in the next video to talk about line types.